Oh, yes, thank you, yes. Very good, okay, cool. Thank you. Yeah, I completely forgot. So, is this good with the log x? Any questions? I can't remember the context, but it seems like a good thing to talk about. Oh yeah, I remember what's going on. I do remember exactly how this came up. Well, just for the record, these are the power series you should know. So as far as the exam is concerned, you can derive any of those. Those come up so often, it's worth memorizing those. So when we first had the Taylor formula, we figured out, well, first we did e to the x. And the second one we did was sine x. And you have it memorized yet? You know the Taylor expansion for sine x? I'll tell you. First, well, actually, let's back up. Do you remember even and odd functions from your pre-calculus or your algebra days? So an odd function is one that has a symmetry about the origin. And the classic example is y equals x cubed. And it's just interesting. It turns out that any function that has only, any polynomial that has only odd exponents is going to be, the graph is going to be symmetric about the origin. And that extends to this. The sine x graph is symmetric about the origin. So in the power series representation, it's only going to have the odd exponents. We worked it out by hand. That is the power series for sine x. And then I asked you how I could use this to get the power series for cosine. What I suggested is taking the derivative of both sides simplify this. That should be consistent with what you believe. Is the cosine graph is an even graph. It's symmetric about the y-axis, and all polynomials with only even exponents are going to have that property. So then somebody asked me, it's a great question, another way that I could use sine to get the cosine, is thinking back to my trig class. So if this is the angle x, what's cosine x? A over c is adjacent over lines. But I could also get that A over c from the perspective of this angle. So if this angle is x, and that's 90 degrees, what's this angle? 90 minus x. Or in a calculus class, we have to call it pi over 2. So I can get that the sine of pi over 2 minus x is also A over c. So if I substitute a pi over 2 minus x in for x, then it'll turn the sine into a cosine. So we're going to use that idea with our original sign here. Does anybody remember who asked this question? Okay, it was a good question. So this is what you were asking, right? Okay. So there's lots of relationships between sine and cosine. The one I was exploiting was the derivative, but a different one can be made by a substitution. So we're going to use this identity. To get cosine x, I put pi over 2 minus x into the sine. So I'm going to call this a sine of q. We know this is cosine of x. And what I'm going to do is, I like my power series to look like x minus something. So I'm going to write this slightly different. So what I have is, this is a power series for cosine. You contrast this with the one we just derived. What's the difference? This is a different center. So this is the Taylor series for cosine. Well, let's just call it the power series with center x equals pi over 2. And this is the power series for cosine with x equals pi. So later in today's lecture, we're going to be, similarly not here, we're going to be approximating cosine x by just taking a finite number of terms. Thank you. By just a finite number of terms. And we're going to see that this is what we want to use if we have angles close to pi over 2. And this is the approximation that we want to use if we have angles close to 0. Is that going? That learning how to approximate functions or approximate values that you're trying to calculate is useful to scientists and engineers. And there's a whole branch of mathematics devoted to that. So at four-year schools, there's a year-long, 2-semester sequence talking about how to do approximations. And there's one more that I want to do. Anybody know the antiderivative of e to the minus x squared? And the best part is nobody's ever been able to find an antiderivative, and mathematicians have proved that there is no antiderivative. So that is an impossible problem. talked about, the very first part of this course was finding antiderivatives, which we could use to approximate or to evaluate integrals. And then we talked about if you can't find an antiderivative, we learned some approximation methods. What were some of the approximation methods we had? The right-hand rule, left-hand rule, midpoint rule, trapezoid rule, Simpson's rule. I'm going to show you another approach to approximate integrals like this. So do you know the power series for e to the u? You should. When's your test? December 5th? 4th? 6th? In not too long of time, you will be tested on all this stuff. One thing that you want to know, actually, I can tell you right here. December 5th. And today is?
14th.
The 14th. Wow. Cool. Yeah, it's like 3 weeks. Oh yeah, I forgot. So yeah, it's